Alright, hell yeah. So today I try to mess up my limits of integration. And I learn a lot, and I learn that you can't. You know what I mean? So that's what we do. So we actually spend half the video doing it twice, like correctly, and then we spend the rest trying to mess up our limits of integration, and we thoroughly do. And then I thoroughly understand why, you know what I mean? You have to get your limits of integration right. And yeah, there's not 4 different ways to set up your limits. For a double integral, there's only 2 different ways. You know what I mean? You can integrate the first term, you know, or the second term. You can switch these. You can do these in either order, but definitely they have to have the correct limits of integration, and that's what we go over. So anyway, thanks for joining me. Hell yeah. Alright, hell yeah. So what we're going to go over today is double integrals. And I'm going to set up the limits of integration 4 different ways. 2 are nonsense, but it's kind of cool because, I don't know, it's just kind of cool. And it gives you a whole overarching view of what the hell's going on. Anyway, alright, so we have this equation that's y is equal to the square root of x. And we want to find the area within this region, and it's kind of bound between x. This is the x-axis, this is the y-axis, and it's bound between 0 to 4. Okay. So what I'm going to show today is that, hell yeah, you have this dA, and in a lot of physics books, this is how I got on this kick, is that you're given this integral. The integral of the region, you know what I mean, of a small little, so usually you're given like a bean size shape, and you're trying to find the area of this region, and then they make a small little, they call it an element. It's a square, and you have a little dA. I guess it doesn't need to even be a square, it just has to be something small. But if it is a square, it has dimension. You know, we could say that this is the x direction. So what we're going to do is, you know, go across. So we have that element, and we're going to say this is a thickness dx, and this is a thickness dy. Now, what I'm getting at in this video is that dx and dy are really small. Like, you could approximate yourself just by, you know, making it 1,000th of whatever unit. You know what I mean? Let's say this is inches, 4 inches, 2 inches. You know, just make it 1,000th. And if all your little boxes are 1,000th of an inch, that's hella small. You know what I mean? So if you added all those up, you'll probably be pretty accurate in getting the right answer. And so, in theory, you would also say that dy would also be 1,000th of an inch. There's no reason why you would say this is 1,000th of an inch, but this might be 5,000ths or any other number. You just wouldn't do that. And so that's what I'm getting at with this idea that dx and dy don't just stop at 1,000th of an inch, or 10 to the negative 6 inches, or 10 to the negative 100 inches. It just keeps on getting smaller and smaller. You know, infinitesimally small. I don't like that aspect of, you know, I think you lose sight. After about 1,000th of an inch, you're like, what's going on? But I guess all I'm getting at is that dx and dy are going to be the same dimension. And so that's why I just did d star. You know what I mean? So this is d star there, d. So they're the same. You know what I mean? So the same. So this area, this little area of dA is going to be d star times d star, or d star squared. So that's what I have. I have what you would commonly see, this double integral of dx dy, which we'll do in a second, can be written as the double integral of d star squared, or just d star d star. And so, so now let's set it up how you would, but see how you can get 2 other ways to solve it that are, I guess, would be nonsensical, but are, it's, yeah, and we'll go over that. Okay, sweet. So, typically how you would solve this is you're like, hey, I have this little wedge of dx, you know what I mean, but it's a distance away in the x direction, some variable x. And up here, this dy is up some distance dy. Okay, so when we set up our integral, if I have this dx first, okay, what I'm going to do is I'm going to vary this dx along the x-axis. So I'm going to take this little square and just move it over here, over there, all the way till I get up to an edge. Okay, I can't add over here. That's not part of the area, and I can go this way. Booyah, and I can get up to that edge. Okay, so these edges are bound by, you know, two equations, I guess. And so, but what we're going to do is we're going to move this box in the x direction, starting from there to there. So, for sure we're going to add up all the boxes till we get to x is 4. Now this one's a little bit trickier to see because we don't start at 0. We run into this kind of this wall right there. And had we chosen a box up here as our dA, you know what I mean, we would have run into that wall right there. You know, run into this equation. And so, we have to say that so let's see, what is our equation? Our equation says y is equal to the square root of x, or x to the 1/2. And what did we put over here? This was x is equal to 4. So I have x is equal to 4. So I must have to put x is equal to something right here. You know what I mean? Do I start at x is equal to 0? No. But on this equation, so I need to rearrange this equation. Basically square both sides. And that will give me x is equal to y squared. So that's what I'm starting at, is x is equal to y squared. Cool. So, so that's adding up all of these squares from that little wall all the way over to here. And these are equations. This equation is x is equal to 4. That's a vertical equation. And then this equation is x is equal to y squared. Okay, and then we would integrate along those terms. And once we do that, we would get this slice, and we finally get, you know what I mean, some sort of area. It's still a really small area because we still have a dy width, which is supposed to be infinitesimally small. So still, this area, you know, ain't nothing because it's just a really small slice. Okay, but then we take this area and we integrate it from there to there. And so that's this dy term. So we have dy, and then we move it in the y direction, starting at y is equal to 0. So this will have a y is equal to 0 all the way up to, and for this problem, we don't really use the equation. Well, you could say, well, we run into this wall right there, and then we keep running into the, well, you know, this slice. We would want to add that last slice. So this slice we could add right here. We could add that slice. We could add this first slice down here. And then the last slice that we would add would be right up against this equation. And that's going to be y is equal to x squared. So we would have y is equal to, I'm sorry, the square root of x. And we have a value for x that we would put into there, and that would be y is equal to the square root of 4. So that's our upper bound on that. So we're taking this little slice and we're going from 0 to 2. Alright, cool. And the reason we can do that this way, we just say 0 to 2, is because, hey, this slice is going to vary as we do that. Because this slice, as you'll see in a second, is an equation. You know what I mean? This slice, the area of that small slice, is different than the area of that slice, different than the area of that slice. Alright, hell yeah. So let's do it. So our first integral is just dx, evaluated at these two limits. So that's just going to be x evaluated at 4y squared. And I can just do this on the side. It's just 4 minus y squared. So that's what we're going to get here. So we're still going to have this part and then this dy. So we have y is equal to 0 to y is equal to 2. We're going to have 4 minus y squared. That's what we got for that first integral. And now we're going to have dy. And now you can see that, hey, that slice, yeah, is this equation. So as we move from 0 to 2, that's going to add different amounts of that slice. All right, hell yeah. So let's integrate this. We're going to get 4y minus 1/3 y cubed. These are our limits of integration. And this is just going to be our area. Hell yeah. So we're going to get 8 minus 2 cubed is 8, so 8/3. 8 minus 8/3, that's going to be 24 minus 24/3 minus 8/3. That's going to be 16/3. Okay, hell yeah, and that's going to be our answer. And so that was putting this dx first, and we can do the same problem doing the dy first. And then we'll get into doing it the 2 other different ways, which probably aren't even worth watching because it's just mixing up. Like all you're doing is you're trading places for the dx and the dy. We'll see that in a moment. Okay, so we're going to do integration. Now we're going to do this dy slice. And if we have this dy slice, we have a distance y to that, and our limits of integration are going to be from 0 up to where it hits this wall, and that wall is this equation, y is equal to the square root of x. All right, hell yeah. And then once we get, so that's going to be all these boxes from here up to there. And once we get that, then we're going to take this dx slice, a distance x away, and then our limits are going to be from 0 to 4. You know what I mean? And hell yeah. So x is equal to 0 to x is equal to 4. And we're going to get the same answer. So, but yeah, let's kick through this. So we're going to integrate this. This one's going to be, this is going to turn into y evaluated at those limits. So we're just going to have x to the 1/2. You know what I mean? This is just the square root of x. And then we're going to have dx 0 to 4. Now we're going to integrate this. This is going to be x to the 1/2 plus 1, which is the same thing as 2 over 2. And then divided by 1/2 to the 1. So we're going to have evaluated at those limits. So we're going to have x to the 3/2 divided by 3/2. That's 2/3. Cool. And then evaluated 0 to 4. When we have a fraction, we could either take 4 cubed first. You know what I mean? We could go 4 times 4 times 4, which is 16 times 4. That's 64. And then we would take the square root of 64. Hey, that's 8. Or you could take the square root of 4 first and then cube it. Square root of 4 is 2. 2 cubed is 8. So 2 different ways to get there. And then, so we're going to take that 8 multiplied by 2. That's going to be 16/3. And hell yeah, we got to check on reality. Okay, so now I'm going to go over to see if this even makes sense. I really haven't even thought this through. But yeah, let's do it. So what I wanted to do was say, hey, I have this little chunk dx, but instead of moving it along the x, you know, taking this box, and instead of moving it this way, I just want to take this dx chunk and then move it this way in the y direction. So what we're going to do is this, the area is the double integral. I'm going to take this dx chunk, but I'm going to move it in this y direction. So I'm going to take it from 0, y is equal to 0, to y is equal to the square root of x. Cool. And then I'm going to take, yeah, let's see if this even makes sense. And it doesn't, and I probably shouldn't have even made this video. Because, like right here it might make sense. But, I mean, all we're doing, if I'm saying this is the dx and I'm moving it this way, I'm really saying that this is the dy. You know what I mean? Because if I have the dy, this little dimension dy, I'm actually taking this dy and moving it in this direction along this y, you know. So, yeah, that's where I made this video, because I was just like, well, can't you do it 4 ways? And probably not. I mean, you could do it 4 different ways, but you would just be... and I think your limits of integration actually have to match. Because if I'm saying that if I'm integrating dx, I'm going to get something x, and I'm going to evaluate it. No, I could still throw in those, but yeah, I don't know. It's just kind of funky. But let's try it out. So we're going to do this first one. I think once we get our slices, I don't think it's going to make sense no more. No, it does. Because, yeah, we're going to take this dx term, and then we're going to integrate along the y, and we're going to get the area of that vertical slice. But then we're going to take this dy term. See, that's the nonsensical part. And because we would have to integrate over the x bounds. You know what I mean? Okay, so I think I see my error, and this is not a good way to do this. But at least we made a video. And but that's just the thing. It's just like sometimes I want to hypothesize something, and you're just like, why couldn't you just take this dx chunk and then just move it in the y direction? Why couldn't you take dx and then have your limits from y is equal to 0? So let's try it out. So we're going to integrate this. It's going to go to x evaluated at square root x, 0 to square root x. So now we just get the square root of x for that. So we have square root of x dy. And then our next limit of integration, well, we would have this little slice, but then we have to take this slice that we've already taken and multiply it by dy. See, that is the nonsensical part. So that's where you could mess up and be like, well, look at this, look at the area of this slice. You know what I mean? This is still an area. Yeah, so that's kind of interesting. Even though you have this like this dA, this differential area. Alright, hell yeah. So yeah, so we have this vertical area, and we can't just multiply it by dy. I mean, we can multiply it by dx and move it along the x terms, like this is going to be x0 to x4, but multiplying it by a dy is nonsensical. But we can say that dx is equal to dy and is equal to d star, so you could mess up like that and just be fine. Yeah, so I think I'm gonna be all right with this because yeah, I think the way to be all right with this is, yeah, let's try to like end it with a bang. Because obviously what I did at the beginning, I couldn't take that little dx slice and then move it vertically. You know what I mean? So there is this idea, I guess, in integration that you got to take that little slice and move it along. You know, if this is the slice from like x is equal to you know, 2 to x is equal to 2 plus change in x, where change in x is where the delta x goes to 0. I'm bad at setting up limits, but hell yeah. Where this just, you know, this is still along the x-axis, and then we're going to move that along the x-axis. So if this is my slice that has a width that is defined by the x-axis, I got to move it along I got to add all those slices along that same axis. I can't just say, hey, I have this little slice, and then I'm moving it. I can't say I have the slice in this direction, and then I'm moving it vertical. But that's the same thing as messing up and saying, well, hey, this slice is just d star. But hey, you might just be confusing it with this slice up here, which is dy. And yes, you can take that little box and then move it vertically. But you're not using a dx, you're actually using a dy. So, cool. And I guess I do like to do videos like this, like kind of go down dead ends and explore them to see like why you can't do it that way. Because I'm sure I'm not the only one to be like, hey, why if I have this dx slice, can't I just go vertical? Well, I think we spotted the error. But if you say that the dx slice is the same size as the dy slice, you really can't mess up. So yeah, let's do it the original way and try to mess it up, you know, or just use the d star, and we'll see if that works. All right, hell yeah. All right, so last round we're gonna do it like we did at the beginning, And so we're going to take this dx slice, but I want to have my limits of integration along this y-axis. So I'm going to, this would be my dy slice, this would be my y direction, but I want to take this dx slice. And so, so now, instead of calling them dx and dy, we're just going to call them d star, because now we really can't mess up. I'm going to do my double integral. I said I wanted to do in the y direction, so we're going to go 0 to square root x and d star. So I'm going to take that first little width, and I want to go this way with it. So I'm going to go from 0, all these boxes, up to y is equal to x squared. And hell yeah. So, and then the second one, I want to go into the x direction, and we're going to go 0 to 4. So there you go. And we have these d stars. So we'll do the first one. D star integrates to, well, yeah, it's just kind of interesting, because if, I guess it doesn't really matter. D star just integrates to star. And then I'm going to have evaluated from the limits of 0 to square root x. And then d star, that's going to be for this second integral. All right, let's evaluate this. And so we're going to have 0 to 4. We're going to have the square root of x. Cool, and then d star. I guess this is where you run into the issue, because, well, is this dx? You know, because that's the million-dollar question. If this isn't dx, if this is actually dy, you know, our limits of integration, I guess, yeah, I mean, when we integrate this equation, if it's just dy, then we just get square root xy. But if it's if this is dx, then hell yeah, then this actually integrates like you would normally would. All right, hell yeah. So I like this corner that I backed myself into, and let's just assume that it's dy. You know what I mean? And but if it is dy, what does that? Yeah, that's in. Yeah, it does have to match the limits of integration. Because if this would have to be dx, and this would have to be x is equal to 0, x is equal to 4. If this was dy, well, that definitely changes our limits of integration. Alright, so I think I thoroughly backed myself into a corner. Oh, this is so interesting. No, this is so fascinating. So, yes, if this is dy, and these are the limits of integration, we can integrate with dy, but we have to change these limits of integration. This has to be y0 to y is equal to 2. And and this becomes a constant, so we're going to have a y. We're going to have the square root of x and then y evaluated, and maybe I have to evaluate both, you know what I mean? And so we're going to see. So we're going to evaluate x is equal to 4, y is equal to 2, and then from y is equal to 0 to x is equal to 0. If I get 16/3, I'll be impressed, because we did something that, yeah, is just fascinating. Alright, so we're going to have 4 square root 2. So we're going to have 8. So hell yeah. For that first term, minus, yeah, I don't think we're going to get anything right now. Alright, no. Yeah, minus, yeah, we might. And then we're going to have minus, 0. So, nope. Yeah, we definitely struck out on that. Alright, hell yeah. So, damn it, this video was not worth it. But I definitely learned quite a bit. So, I don't know. I don't know if a video of just going down a dead end and exploring something is worthwhile. But that's what we did today. And it wasn't worthwhile. We at least did it twice the correct way, and then tried some nonsense. And the nonsense did not prevail. So, sweet.